Okay, it's fine.
I'm sharing the chef first.
So, welcome to the last section in the afternoon. The first speaker is Dario Daghero, who will tell about point contact spectroscopy in iron-based superconductors.
Thank you, Lara, and thank you everybody for being here, in spite of the fact that the match is going to begin. Not very well. Anyway, my talk will be about point contact spectroscopy in iron-based multiband superconductors. And my original idea was to give an overview of what we have, not only us as a group, but of what the point contact spectroscopy has been used to do in iron-based compounds. But then I had to focus on only two materials because there were too many data to show. Then these are the people of the group in Torino who have worked in these activities. So Mauro Cortego, Sara Galasso, Paola Pecchio, Giovanni Marino, and Antonio Mendy. This research is partly funded by the European community through this joint Europe-Japan Iron Sea program. Well, this is a long list of people who have collaborated in some respect for the calcium crystal, Karpinski, Chicago Bukowski, for 3 films of iron, selenium, tellurium, Atsutaka Maeda and Yoshinori Mai from Japan, and Ichiro Tsukada for single crystal of iron, selenium, tellurium. Valery Stefano, who has collaborated with us for point contact measurement, and Roy Van Kramer in Max Planck in Stuttgart for the high pressure setup that has been used for some of the measurements. Gianni Corteta for DFT calculations, and Dr. Suzuki for Japan again for an orbital model plus random phase approximation calculations. You will see the reason why there are so many collaborators. Well, the idea of my talk is the following. Point contact under real reflection spectroscopy is a tool that is, in some sense, traditional for the measure and for the investigation of superconductors. But with the discovery of multiband superconductors, and in particular with the discovery of iron-based superconductors, a huge effort has been made to refine the technique. Actually, not exactly the technique, but rather the tools they used for the analysis of the spectra, so as to extract information about these systems that are complex. Here, I will show some recent, still unpublished results of our group in iron, selenium, tellurium, and calcium on 2 under pressure, and in which all the capabilities of the point contact spectroscopy have been exploited, and in particular its sensitivity to the symmetry and the structure of the energy gaps or of the parameters that you prefer, its sensitivity to the electron boson coupling, and its sensitivity, which is in some sense only qualitative, to the topology of the surface. Well, point contact spectroscopy is a very simple technique, though powerful but very simple. It consists simply in making a small contact between a normal metal and a superconductor. We use what's called the soft technique, in which there is a gold wire which is stretched across the sample surface and which is kept in place by using a small drop of silver paste. In this case, the contact is actually not only one, but it's a network of contacts established between single silver grains and the crystal surface. Note that so this is a sort of a special average of the signal, and this technique, this setup allows high contact stability in temperature. It still allows to control the resistance of the contact by applying short voltage or current pulses that change the network of nanocontacts, and also it has the unique capability to be used also when the sample is enclosed, for example, when it is in a pressure cell, which is essential in this case. Well, anti-reflection is, of course, the mechanism that allows point contact to measure the gap. I will skip the details. The important thing from our point of view is that in the very ideal case where we have one directional injection, where we have an S-way superconductor, T equal to 0, and so on, we expect a doubling of the conductance of the junction in an energy range that goes between minus delta and plus delta. Actually, in the real case, the spectra never look like that, and so we need some tool to fit the real spectra to obtain the gap. Actually, what we want is the expression of the conductance in terms of the fundamental quantities, and then let's start from probability of transmission. It is the sum of these 3 terms. This is the probability of Andreev reflection. Andreev reflection is just the reflection of an electron whose energy is smaller than the gap as a whole, while a Cooper pair is transmitted in the superconductor style. And this is the probability of normal reflection. The spectrum, which is this one, is simply the ratio between the probability of transmission in the superconducting state divided by the probability of transmission in the normal state. The problem is depending on how I express explicitly these quantities, I have different models. The first model was the 1D BTK model. It dates back to 1982. It's for only one direction of injection. So it can be used only when you have an isotropic order parameter, because you lose completely the dependence on the direction. The 2D BTK model, which is the one which is mostly used in most of the papers, can account for an in-plane anisotropy like in cuprates, but it has also 3 parameters. Normally, this is also used for MGP2 and so on in a multi-band case. So in that case, the contribution of different bands is simply summed with a weight which is specific for each band. But this is also only an approximation. This is not exactly true. Okay, this is true only in an approximate way. And the most important thing is that both the models are based on the assumption of spherical Fermi surfaces. And this is clearly not the case of ion-based compounds, where the Fermi surface is neither 2D nor completely 3D. And so we generalize the BTK model to the case of a, let's say, arbitrary shape of the Fermi surface. Don't be scared. These are the last formula I will show. Suppose that we have the 3D BTK model is intrinsically multiband, because you can have as many bands as you want. Suppose this is the Fermi surface, the Fermi surface sheet, then this is the direction of current injection, in this case it's vertical. Then the normalized conductance is expressed by this ratio. Here you have a sum over the sheets of the Fermi surface, and this is an average over the ith Fermi surface sheet. These quantities contain only information about the shape of the Fermi surface, and this quantity contains instead through through these functions here, the information about the order parameter that can have any dependency principle on the weight. So this is the model we are going to use later. Okay. An example is the application of MGP2. It really works, yes, because this is the Fermi surface from DFT calculations. Just for the sake of to have easier calculations, we use a model Fermi surface that keeps the most prominent features of the original one. And then if we associate to the pi band the pi gap from first principle and to the sigma band, the sigma band gap from first principles, we can obtain a spectra that perfectly fit the experimental ones. Of course, here we have additional parameters. That means the Z, which is the parameter that controls the height, the potential barrier between the normal matter and the superconductor. But actually, the shape of the curves is perfectly well reproduced. Note that in this model, in the 3D BTK model, the weight of the different bands is not a parameter because it is given by the shape of the Fermi surface. So. This is just one thing that I would like to remark, is that suppose that you have two Fermi surfaces like this one, and suppose that you have a gap that resides on this Fermi surface, which is almost 2D, and that has vertical line of zeros or vertical line of nodes. Okay? In this case, if you use the 3D BTK model, you see that for injection along the AB plane, you will see a zero bias maximum. The zero bias maximum is the hallmark of this in-plane anisotropy of the gap. But if this is the case, if you inject the current vertically, that means along the C direction, you don't see a zero bias maxima, but a zero bias minimum. This is an effect of the shape of the Fermi surface. So, if we observe peaks in the experimental spectra for injection along the C-axis, and this is the case I will show you later, this means that for sure we are not in this condition. Rather, the condition could be something similar to this one. If the Fermi surface that hosts the anisotropic gaps is closed, is completely 3D, then you have peaks both along the AB plane and along the C-axis like this. Keep this in mind for the following. Okay, these are point contact spectroscopy measurements in iron, selenium, and tellurium films. These films have been grown on calcium fluoride substrate in Tokyo by PLD method. They are very well oriented along the C-axis and in the plane. So, from the point of view of spectroscopy, they look like they are like single crystalline transactions. So we perfectly know the direction of the current injection with respect to the crystallographic axis. These are 3 examples of spectra taken in 30%, 40%, and 50% selenium content. All the spectra show multiple features that so that if you fit the spectra by using a single gap, a single band BTK model, you completely lose a big part of the curves. Then it is possible to fit them by using a 2-band BTK model, and the fit is almost perfect. Okay, then we will plot the values of the gaps extracted from the fit as a function of the critical temperature of each contact. And what we obtain is this one. Well, it's a nice picture. We have apparently two gaps that scale with TC. This is the local TC of each contact. But look here. To delta over KTC 11, a little bit too much. And so this clear that this value is really huge. So we were wondering, but can this be something which is not a gap? So maybe these additional shoulders are not gaps, but we are mistaking them by the gaps, and they are fitting them even though they are not gaps. So to check that whether these structures are actually, these values are actually due to the fit of electron boson interaction structures, we performed some calculation within the Eliasberg model. Why Eliasberg? Because in point contact can detect the effect, the structures associated to the strong electron boson, electron phonon, whatever interaction, but the BTK models do not contain this information. So to be able to see and reproduce and analyze these structures, one needs to calculate the energy-dependent gaps from Eliasberg, put these energy-dependent gaps in the BTK model, and in such a way, the BTK model reproduces these features. For example, this is the case of lead. You see these typical, very well-known fluctuations around the BCS density of state. This is that Z equal to 20 means tunneling regime. If you go toward the Andreev reflection regime, Z equal to 0, you see that they still persist. And in the second derivative, there is a perfect correspondence between the peaks in the second derivative of the derivative of the conductance with the peaks in the alpha square F. And this correspondence is no longer perfectly obeyed in the Andreev reflection regime, but anyway, the structures are there. So we calculate, we use an effective free band. It is not free band the sample, maybe, but the effective free band is the minimal model that can reproduce our results. So we use this minimal free band model, supposing that the coupling is due to spin fluctuations. Okay, I'm not saying that I'm sure that they are, but suppose that they are spin fluctuations. So the Lorentzian shape is mimics the shape of the spin fluctuation spectrum. The peak is put at this energy that corresponds to I don't know the name, to this law which has been found experimentally that relates the TC to the energy of the spin resonance. Then we obtain, we need the ratio of the density of state, but this is a detail. We obtain the gaps in such a way that they lie here, okay? So supposing this is really a gap, what is the position of the electron boson structures? And the answer is that this is the curve. So the gap is this one. These are the electron boson structures. And if we fit this curve by using the 2D BTK model, this is the red line, we obtain a gap which is exactly the gap we have put in. So it's the real gap, plus a fake gap at 8.5. So this means that going back to our picture, this is really a gap, this is not a gap. And so we have only one gap that seems to be was to delta over KTC of the order of 6. But here, what happens here? Because we have blue and red data. This simply means that in some curves, we do not have a very big structure associated with the electron boson coupling, but we have very clear structures still associated with the two gaps. So it's possible to fit the curve with two gaps, one here and one there. Well, this is complicated. Then what is the real gap? In single crystals, the electron boson structure is much lower, and the signal, the superconducting signal is much higher. But anyway, we can fit this curve with two gaps, and the two gaps lie one here and one there, one here and one there. So in the end, it turns out that we actually are in this condition. There are really two gaps. They are not seen at the same time always. Sometimes you see the small one and the boson. Sometimes you see the large one and the boson. Sometimes you see the small one and the large one together. And this scale we can see in this way. Are these data, note that this is, as far as I know, this is the first analysis of this system as a function of doping, or TC if you want. If you plot the data from literature, there is a very nice agreement. In particular, these are data from STS. This is the recent paper by Yin group, Dr. Pan's group. So this one and this one, okay. And these are data from ARPES. They see three gaps, 1.7, 2.5, and 4. We cannot distinguish between these two small gaps, this one and this one, but the large one perfectly fits in our picture. So By the way, all these fits have been done by using isotropic gaps, so we do not have any clear evidence of the fact that the gap is anisotropic. So the fourfold oscillations in the gap observed by angular dependent specific heat apparently do not appear, but they neither do they appear in Atlas measurements. So the reason of this disagreement is not known to me. Well, let's go now to calcium 122 under pressure. This is the phase diagram. At ambient pressure, calcium 122 has a tetragonal to orthorhombic phase transition, which is associated also to the onset of the antiferromagnetic phase. In hydrostatic pressure, it shows a tetragonal to collapsed tetragonal phase, the one that has been already described by Dr. Paglione. In this phase, as already said before, there is no hole-like Fermi surface around gamma. There are no spin fluctuations. This has been proved experimentally and also calculated. The magnetic moment is completely quenched, and there is no superconductivity. But this system is superconducting under pressure, provided that the pressure is not completely hydrostatic. If you have at least one uniaxial component, you can observe the superconductivity, and this superconductivity is always confined to a small volume fraction, as we have seen before, and it's thought that this superconductivity is associated to a non-collapsed tetragonal, but to a tetragonal phase which is not collapsed, which is still paramagnetic, and that hosts superconductivity, as I said before. And this T prime phase coexists with the collapsed tetragonal phase. These are XRD data. You see that this is the orthorhombic, this is T prime, and this is collapsed tetragonal phase. So we are wondering, what happens here? What is the Fermi surface here? What happens to the gap here? What are the characteristics of the superconducting phase in this case? Then this is the mounting of the sample. The sample is in a pressure cell. The liquid, the pressure transmitting medium is silicon oil, which applies a hydrostatic pressure at room temperature, but when it freezes, it applies a pressure which is no longer hydrostatic. And this is what we need because we want to observe superconductivity, of course. This is a sketch of the mounting inside. These are two examples of spectra. These are, as far as I know, these are the first spectra of point contact measurement ever taken in a sample under pressure, because mounting is absolutely not trivial. And this is for 0.4, this is for 0.6 gigapascal. You see that all of them show a zero bias maximum plus shortest. This is very similar to what I have shown before. So this is suggestive, by the way, the current here is injected along the AP plane. This is suggestive of an anisotropic order parameter. But what happens if we inject the current along the C-axis? Because this is the final test. If we inject the current along the C-axis, we still see the same structure, the zero bias maximum plus additional structures. So for sure, the Fermi surface that hosts this gap, the small gap, which is anisotropic, is not too big. And so to go further in the fit of the curves by using the decay model, we need the DFT calculation of the Fermi surface and calculation of the order parameter structure to know exactly what is the shape of these nodes, okay, or zeros. Okay, these are then structure calculation calculated by Gianni Profeta, made by Gianni Profeta. You see the total energy in red and black, and the magnetic moment in blue as a function of the C over A ratio. That means moving from here to here, I'm compressing the C-axis. Okay, this is what the uniaxial pressure does. There is a first minimum in the total energy. This corresponds to the orthorhombic antiferromagnetic phase, and the magnetic moment is of the order of 1.5 MeV. When the pressure is increased, you find a second minimum, which is the collapsed tetragonal phase, and you can check that the value of the parameter is perfectly in agreement with what found in hydrostatic pressure. But there is also this region which separates, which corresponds to the very fast disappearance of the magnetic moment and the transition towards the collapsed tetragonal phase. We suppose, we believe that here, the superconducting region lies here, so the structure that hosts superconductivity must be necessarily here. It can be here, it can be there, but it may lie in between. So as a representative of the structure, we took this point here, T prime. And what is the Fermi surface in T prime? Again, we are on the verge of a Lipschitz transition, because this is the antiferromagnetic phase, this is the collapsed phase, and this is T prime. So the Fermi surface is going to split into separate pockets. And this is very interesting because it, again, is in agreement with what we have seen before. And this is just a picture of the band structure. You see that there is a progressive disappearance of the hole-like band around the point gamma. And then, now we know that this is the Fermi surface, but and we know that this Fermi surface must host also gaps, one more or less isotropic and the other one which has probably an in-plane anisotropy and has some nodes or zero, we don't know exactly. So what is the expected structure of the gap? We asked Dr. Suzuki to perform calculation within the 10 orbital model plus random phase approximation. This is a vertical cut of the Fermi surface. These are the hole-like Fermi surfaces. These are electron lights. This is a horizontal cut. You see that these are the maps of the gaps. You see, for example, here, in the first, on the top of the Brillouin zone, you see that the gap on the electron light, these are the profile of the electron light Fermi surface, is almost isotropic. On the black one is the hole-like Fermi surface profile. Here the gap has a fourfold oscillation, so it's anisotropic in the plane. But it has everywhere the same sign. The lines of nodes are the red lines that lie far apart from the Fermi surface. In the second cut, here, we have almost the isotropic gap on the electron light Fermi surface, but on the hole-like Fermi surface, the line of nodes is touching the Fermi surface. So here we have nodes that touch the Fermi surface. And on the third case, in the third cut here, again, same thing, almost isotropic gap here, and here the gap has completely changed sign. So we have a line of nodes at pi, at kz equal to about 3 or 4 pi, and here we have almost a horizontal line of nodes. So this is the Fermi surface. I did not show the gap because it is difficult to draw, but we mimicked this by using a model Fermi surface. It looks completely different. It is only due to the fact that for clarity I changed the proportions, and this is only the top half of the Fermi surface. Okay, this small cylinder here is neglected because for C-axis injection it absolutely has no effect, no weight. And for A-butane injection, it has a very small weight, a small surface. So by using these, by the way, this gridded surface is the gap. You see that it has a fourfold oscillation, but it has no vertical nodes, and the nodes like here where it crosses the Fermi surface. With this geometry, we can put everything in the 3D BTK model and see whether we can fit the data, and the fit is very good. At all pressures, 0.4, 0.6, 0.8. We actually have 9 different cases, different pressures, and the fit is always rather good. It is also possible to determine the temperature dependence in particularly happy cases. Okay, here you see that these are the gaps. I would not square this really because I don't have the very good evaluation yet of the uncertainty, but it seems that the gaps are both depressed below the so-called, let's say, BCS-like behavior. And especially, the fit works also for C-axis injection. And this is very important because it's a proof of the internal consistency. Note that the fit, we have tried with many different, to change a little bit the shape of the Fermi surface, the position of the nodes, and so on. And the fit, this configuration, which corresponds to the one found by calculation, is the one that allows the best fit. So in the end, I can report the values of the gaps, of the gap amplitudes, as a function of the pressure. You see, this is PC. And the gaps, this is the electronic gap, this is the holonic gap, they follow more or less the trend of the TC. But they, in correspondence to the pressure range between 0.5 and 0.6, they increase more than the TC. So the result is that if you calculate the 2 delta over KTC ratio, you see an increase in delta over KTC in both gaps above the BCS value. So it seems that really on the position in the pressure where you have you are going towards the collapsed terminal phase, so you are on the verge of a Lifshitz transition, it seems that you have a boost to superconductivity. I don't know really how to imagine this, but for sure this is something which is very interesting in the picture we were saying before. So the natural question is what happens in so what is the role of spin fluctuations in this case? So are really spin fluctuations are responsible for the pairing, or they do not have anything to do with pairing? And And this is again similar to what both Borisenko and Bianconi have said, and also Paglione. So, in the conclusion, in iron, selenium, tellurium, you find evidence for two gaps without any clear evidence of anisotropy, plus a huge electron boson interaction contribution. This electron boson interaction really has an energy that corresponds to the energy expected for spin fluctuations at this T. For calcium 1-2 under pressure, the point contact itself alone suggests an anisotropic gap that resides on a non-2D Fermi surface. Then we have done many calculations by DFT and by an orbital model, and we have really confirmed that the Fermi surface that hosts the anisotropic gap is on the verge of a topological transition, let's say a Lipschitz transition. And the gap really has nodes, but it has an in-plane line of nodes. Sorry, a horizontal line of nodes. This information allows to perfectly fit the curves. And by the way, I would like to remark that this is a very complex, let's say, set of experimental and theoretical technique that, in principle, it is very powerful. So, in principle, it could be used also to analyze other compounds, like those shown by Professor Paglione before. Open issues and future prospect. Okay, open issues, there are many open issues. The one is, why don't we see any anisotropy in the gaps? Also in cobalt doped barium 1-2, many measurements, for example, the measurements of Raman's scattering, directional specificity, see fourfold oscillations or loops of gap minima. We never see something like that. We don't know why. Either our technique is not sensitive enough, but also ARPES, for example, does not see any oscillation. So this is an open question. Probably it's a difference between, I don't know, but I am asking. Difference between bulk and surface, so I hope it is not the case, but maybe it is the case. Then another interesting thing that would be done is the study of phosphorus doped barium 1-2 and lanthanum 1-11-11, because we would like to check the prediction about the emergence of nodes as a function of the doping that were made exactly by Dr. Suzuki. And another interesting thing could be the investigation of compounds like the rare earth doped with calcium 1-2 to understand what is the superconductive phase. Also in this case, there is a T prime tetraeder non-collapsed phase, or other compounds with no nesting, no Fermi surface nesting. Like, for sure, point contact on this compound is out of question. In single layer, it is not possible. But in these layers, in this compound, maybe it would be interesting. And also in this one that has a strange double dome in the superconductivity. It is maybe very interesting. But we are open to any question and any suggestion for future developments. We have this technique. It is not ARPES. It is not as powerful as others, but it is very simple in principle. It can be used in many compounds. Thank you very much.
I want to say that in 1-2, cobalt doped 1-2 in ARPES, there's big difficulty to see the gap at all. Until now, there is only one publication, and people suspect that the surface property in this particular case is such that it's sort of difficult, not to mention an iron isotrope. And in iron selenium, the Fermi surfaces are so tiny that it's also very difficult to see. These technical things.
Okay.
I have a question actually. You showed us this electron boson feature coming up in the experiment, but it can show up or not. So what is the condition that makes the electronic boson to show or not?
Imagine for a moment that this does not exist. Then if you compare these curves here, okay, it's rather strange. I don't know the reason, but if you look at more or less, this structure has an amplitude of 0.1, more or less. But the superconducting signal as a whole is not greater than 1.15 in fields. In single crystals, the height of the boson is the same, but the signal is almost 2. This goes to 1.3, this goes to 1.19, so it's the almost ideal SN junction. So I don't know the reason why this should have almost always the same weight, but it's the fact that the superconductivity signal in crystals is much higher. This curve is an exception. This one, I have no explanation why. You don't see very clearly this picture. I don't know.
But in the theory, what do you do to see or not the? So you don't have a specific parameter.
Ah, you mean in the theory? No. Well, yes. We have made different calculations. You can make these shoulders more or less evident by changing essentially the lambda, because you have different two lambda, which are free parameters. By tuning lambda 1,3 or lambda 1,2 in a different way, you can make them more or less visible. But it's a fact that also in reality they can be more or less visible. That I don't know why.
So in the experiment there is a clear difference between films and bulk.
Yes.
In the theory you just choose the parameters.
This was just an example, of course,
okay.
just to show that if one gap is 3, the electron coupling can be mistaken by a gap which is about 8.
And if you go to delta plus boson energy, the peak would be delta.
Yes,
plus
of course. Yes, of course. Yes. Delta plus 1.
Yes.
So I guess I sort of missed it. Was the pressure that you're using to calculate the superconductivity is uniaxial or hydrostatic?
Actually, it is the pressure measured by measuring the superconducting transition of a piece of lead which is mounted below the sample. So, just below the sample we have a sort of succeptometer. Okay. Here. And we measure the transition or temperature of this lead, and there is a very well-known dependence of the transition temperature on the pressure. Unfortunately, we have no way, at least as far as I know, to determine what is the amount of uniaxiality and the amount of hydrostaticity. Unfortunately, this is the strong limit of this kind of experiment.
And the reason I ask is because there's some common idea that there's no superconductivity under hydrostatic pressure.
Indeed. If you use helium, you would not see any superconductivity. And this is the reason why we use the silicon oil. In helium, it would be much easier to measure because you don't have the oil on top.
Actually, BKT transition, right?
BKT? No, I'm talking about BTK, the logarithmic clustering model. No, it's not a topic. I didn't specify it.
Okay, so thank you again, Dario. We move to the next.